Most of Chapter 9 is not going to be on the AP exam, and since it's not on the AP curriculum, we're just going to not cover it for this. But there is one important section, and that's called hybridization. And you did not do this in honors chemistry, and you're going to do it a ton in college chemistry if you take it. So I want you to be familiar with it. And let me just give you a little overview about what it means, and then I'll show you how to figure it out for each compound. Here we go. So the first thing is, if you look at methane, which is CH4, notice that C tends to form 4 bonds because it has 4 valence electrons, so it has room for 4 more to reach that magic number of 8. So if you write out the electron configuration for carbon, you end up with 2s2 and then 2p2. So this is the electron configuration for carbon. So what that says is that we have 2 electrons in the s orbital and then 2 in some of the p orbitals. So if you plot the energies, notice over here on the graph, the s electrons are actually at a lower energy than the p. So it goes in order. S is the lowest, and then p, and then d, and then f. So f is a higher energy than the rest of them. So what that shows us is that if we go purely based on the electron configuration for carbon, that we should have 2 different energies, one for the s electrons and one for the p electrons. But all of the studies that scientists have done when they study methane show that all 4 of those bonds actually have the same energy. And so the theory that they use for this, the idea that they came up with, is that those electrons and those orbitals, and an orbital is a fancy way to say a region of space where electrons probably exist, that they merge, and a hybrid means kind of like a mixing of things, kind of like a hybrid car can do both gasoline and electric. And so hybrid orbitals have been mixed so that we have 4 of the same orbitals. So notice that we took the 3p orbitals, the 3p spaces, and we took the 1s and we put them all on the same level. So now they're all the same energy, and we spread out the electrons because of Hund's rule and the idea that electrons repel each other. And now notice that we have 4 equal places for carbon to receive electrons and to bond with something. And so when it bonds to hydrogen 4 times, all 4 of those bonds are going to be at the same energy. So this is the idea that you can mix orbitals so that they have the same energy. And so we call this sp3 hybridization because it took 1s and 3p orbitals to make that hybridization. And if you look at this picture down here, you remember how an s is a sphere and p looks like a peanut. It's actually kind of like an infinity sign, but you can see the 2 different lobes and then it's skinny in the middle. And so if you take a peanut, take 3 peanuts and an S and kind of merge them together in terms of their shape, you're going to end up with kind of this lopsided picture right here. And it is important that it's lopsided, and that's because the sphere is part of it as well. And so that's the kind of the model that they use for carbon, so that when carbon bonds to hydrogen, it actually is using these kind of lopsided orbitals to bond to hydrogen. I think I have a picture of this further on. Yep, you can see it down here with the lopsided orbitals. And so that's called sp3 hybridization. And that happens anytime you have 4 effective pairs of electrons surrounding the carbon. And what I mean by that are either a bond counts as an effective pair, or a lone pair. So if you looked at NH3, and I ask you, what is the hybridization on nitrogen? So first of all, we're only going to hybridize central atoms. For this, the hydrogens are not hybridized in this case. So the hydrogens just have their regular old S. And so for nitrogen, we have 3 hydrogens, so 1, 2, 3, plus we have that electron cloud. So we actually have 4 effective pairs of electrons for this nitrogen as well. So this one would also be sp3 hybridized. So again, you're going to count how many things you have bonded to the central atom. And by things, I mean either an atom or an electron cloud. And then once you get your total, you're going to add up however many orbitals you need to equal that. We only have 1 s, so you're done with s once you get to 1. We have a total of 3 p's, and then if we need more, we would continue on to the d's, and we'll do that in just a minute. Let's look at another one. So this structure down here, the C2H4, actually has 2 central atoms. So both of to be a central atom, you have to have at least 2 other atoms bonded to it. So those 2 carbons are both considered to be central atoms. And so if we look at the hybridization, we're going to count how many things are bonded. So notice that the left carbon has 3 things bonded to it. And so we need to start adding up orbitals. So the S only just has 1. And then P, we're going to do 2 because 1 S and 2 P's gives us 3 things. And so those 2 carbons are called sp2 hybridized. So what happens is that the carbon on the left has the sp2 hybridized orbitals, kind of the lopsided things, and then hydrogen has the regular old sphere. This is going to be lopsided and then regular old sphere. And then this carbon is also sp2 hybridized. Let me color them in so you can see them better. So the H is just a normal sphere, and then each carbon, notice that it has 3 of the sp2s. And so then you might be asking yourself, well, if it took 2 of the sps, and you can kind of see that over here, you see how it took 2 of the 3 p's? That leaves behind 1 p orbital that was not hybridized. You can see that in this picture right here, that we took the sphere and 2 of the p's and blended them together so that we had 3 bonds that we could bond it to, and then you have that leftover p orbital, and it's that leftover p orbital that is going to make this the second bond of a double bond. So I'm going to draw it like this. This one has a leftover p and this one has a leftover p, and they're kind of going to attract on the top and the bottom, even though it's only considered to be 1 bond. And those blue attractions are the second bond of the double bond. So the first bond of that double bond is the red hybridized orbitals hitting head-on. The second bond of the double bond is the blue orbitals that are hitting kind of parallel to each other. So that would be sp2. And there's different words for how they hit. So anytime that the bond is going to hit head-on, so if you have something hitting head-on like this, whether it's an S, whether it's a P, that's always going to be a sigma bond. And sigma is going to be anytime you have single bonds and it's the first of a multiple bond. And that's called a sigma when they hit head-on. So back up here in this picture, the carbons are having sigma bonds with each hydrogen because they're hitting head-on. The hydrogen is not hybridized, it's just a sphere, and then the carbons have the hybridized orbitals that are hitting head-on with that. So those are the sigma bonds. In the double bond, the first of the double bonds is a sigma. That's the red hybridized orbitals hitting each other. And then that leftover P, this one right here that was not blended, not hybridized, those P's that are left over on each carbon are hitting each other parallel. And that is the second of the double bond. And that is called a pi bond. So this is the symbol for pi. This is the symbol for sigma. They're Greek symbols. And a pi is just like this right here. So notice that they're hitting kind of parallel to each other. And you actually get 2 regions of attraction on the top and the bottom, even though this is just considered to be 1 bond. So this would be the second of a double bond. It's also the third of a triple bond. So if you had a triple bond, the first one will be sigma. Anytime you have a single bond, it's sigma. And then the second 2 would be pi. If you have a double bond, the first one is sigma, the second one would be pi, and if you just have a single bond, it would just be a sigma. And those second and third bonds come from the overlap of those p orbitals. Let's do one more. So this one is if you have carbon dioxide, I think that was the molecule we're going to use. Yeah, it's down here. So this is what the Lewis structure for carbon dioxide looks like. So if we're looking at the carbon, we're going to see how many things are bonded to it, either atoms or lone pairs, and we only have 2. So in this case, when we blend the orbitals right here, we're going to blend an S with 1 of the 3 P's, which leaves behind 2 extra P's. So notice right here, we have 2 that have been blended that we're going to call SP, and we still have 2 left over regular old P's that have not been blended. You can see a picture right here as well. There are 2 that are not blended and then 2 that are blended. So if we look back at the carbon, the first of those double bonds is a head-on collision with oxygen's bond or oxygen's orbital, and that's going to be the sigma. where you have the hybridized carbon, so it'll be a sp, colliding with oxygen. And then the second is going to be the leftover P's. And notice that we have two of them, so we can give one to one oxygen and one to the other oxygen. And there's kind of a picture down here. So this picture, and there's a better picture in your textbook with this, but you can kind of see the head-on collision that carbon has with oxygen. So here's a head-on collision, that would be sigma. Here's a head-on collision, that's another sigma. And then the carbon has two leftover P's. So one is going to collide right here and here, and one is going to collide right here and here. So one of them they donated to this oxygen, and then one of them they donated to this oxygen. And I know it looks like a triple bond, but the blue areas are actually just one bond. They kind of overlapping on top and bottom. And there's a whole lot of pictures in your textbook that can definitely help you. Also, I posted another video, and it's a really great video that shows some animations and some pictures to help you as well. And then there's just, so first of all, notice that the sp2 orbitals on these two oxygens are at 90-degree angles, as are the pi bonds between the carbon and the oxygen. So the question is, why doesn't carbon undergo dsp3 or d2sp3 hybridization and phosphorus and sulfur do? And the same answer is the reason why it can't hold more than the octet. And that's because their carbon is in the second row. So all of its electrons are in the second energy level, all of its valence electrons. And so it doesn't have an empty d because there's no such thing as a 2d. So it doesn't have that empty d orbital. So here are just some of the things you can look at, sp versus sp2. You don't have to memorize all of this. All you want to do is to just draw the Lewis dot diagram, count how many things are on the outside, and then add up how many orbitals you would need. So the D's are not actually on the AP curriculum. I threw it in there just because I think you can handle it, but you won't see those on the AP exam. They will only have S's and P's. But that would be something like if you had sulfur and it was bonded to fluorine. If it was an octahedral like this. Then if you count the outside atoms, you would have 6. So you're going to have 1 S, 3 P's, that gets you to 4, and then you would also have to have 2 D's, which would get you to 6. But again, you won't see that on the AP exam. And just a couple more things. Most materials have no magnetism until they're placed in a magnetic field, but in the presence of a field, you can tell two different things. And these are just some vocab words that you want to become familiar with. Paramagnetism means that you have some unpaired electrons, and diamagnetism means that they're paired. And the best way to see that is to draw the orbital notation. So, for example, carbon, remember, was 2s2, 2p2 for the abbreviated orbital notation. So we would, or electron configuration. So we would do 2s with an up and a down. And then don't forget that Hund's rule, should be a 2 there. Hund's rule says to spread out the electrons. And so this one, since we have some unpaired electrons, would be paramagnetic because those two electrons in the p orbitals are not paired up. So once you draw all your arrows, if every single one has an up-down, that's going to be diamagnetic. If you have any that are just one direction, that's going to be a paramagnetic one. And the last thing is you can we talked about this with benzene, that you can talk about the sigma bonds and the pi bonds here as well. So this one is... just a reminder about benzene, this is that 6-member carbon where each carbon has a hydrogen. So notice that there's 3 bonds there. And then what happens is you have some double bonds, but because of the resonance that happens, those double bonds kind of get spread out. And so basically it's a whole bunch of p orbitals. So if you have a flat hexagon, I can draw it kind of flat, the p orbitals are going to stick up and at the bottom. And they can overlap like this. So you get that region of overlap among the P's around the top. And sometimes they just draw it like a donut, which is what you can see the delocalized benzene model there. Localized means it's attached to something. Delocalized means it's kind of spread out. And actually both of these are acceptable to draw. But if you look in your textbook, there's some pictures of that you can see kind of a better picture of how those are delocalized. And that's it for chapter 9.